I am Dr. Zaheer, Department of Chemistry, C. Abdul Hakeem College. Today we are going to see one important topic in quantum chemistry, that is Heisenberg uncertainty principle. This principle is also known as principle of indeterminacy, or it is also known as Heisenberg complementary principle. This is a very important topic. Already we have seen some basic thing of this principle in wave particle duality. Okay, let us see that the definition. What is the principle? What is Heisenberg uncertainty principle? We are going to see now. Now, first of all, what is Heisenberg uncertainty principle? It is impossible to measure simultaneously the dependent variables. According to the definition, it is not possible to measure simultaneously, at the same time, simultaneously, the dependent variables. You can get information only about one variable, and the information about the another variable you cannot get simultaneously. So this is the definition of Heisenberg uncertainty principle. And these dependent variables are also called as conjugate variables or complementary variables. So this is the definition. Now we are going to see what are those dependent variables, or we can say conjugate variables. Examples we are going to see. Then we are going to see the explanation by taking each and every example. Now there are three examples, three sets of complementary variables I have given. One is known as position coordinate and linear momentum coordinate along a single axis. You must consider only the linear motion, not the angular one, for the first one. Second one is angular position and angular momentum. And the third one is known as energy and time. Third one is energy and time. So these are the three sets of examples for complementary variables or conjugate variables. We have seen the definition in general, but now we are going to see the definition by taking each and every example. First one is position and linear momentum. So by taking these two as conjugate variables, how the Heisenberg uncertainty principle can be explained? Now this is the statement 1. I am taking position and momentum. This is the first set I am taking. If you take position and momentum, how will you give the definition? It is not possible to determine precisely, exactly, both position and momentum of small moving particle simultaneously. This is the definition, first definition. By taking position and momentum, you cannot determine both position as well as linear momentum of a particle, that too a small particle, simultaneously, which is moving along a particular axis or along a particular direction. Now, I am determining the expected value of position. Expected value. Expected value means theoretical value, I can say. Then you can do the experiment. Already we have seen Compton effect. That Compton effect is also useful for determining the position of the electron. Okay, by doing the experiment, you can determine the position. So that value is known as x bar. Expected value or theoretical value is known as x, experimental value is x bar. Now you find out the value of x minus x bar. So difference between the two values, that is known as, the difference is known as delta x, and the delta x is representing what? The delta x is representing error in the determination of position, or I can say that delta x is known as uncertainty in position. So you might have done practicals in gravimetric analysis, estimation of sulfate as barium sulfate, estimation of chromate as barium chromate. So teacher will have one theoretical value. You will be doing your experimental value. You will be doing the experiment and your value is experimental value. Both the values will not match. There will be some difference. So the difference is known as the error that you have committed in your experiment. You are not certain to that particular value. So similarly, delta x is also known as error. You are committing error, or we can say you are not certain in this position. So you are not certain in the determining of this value, that is known as position. Similarly, you take the momentum. The expected value of momentum is p. The experimental value of momentum is equal to p bar. So find out the value between these two difference, delta p. So similar to position, delta p is also representing error committed during the determination of momentum, or the difference is equal to uncertainty in momentum. You are not certain to that particular value. So error in the determination of momentum or uncertainty in momentum. So now we have seen what is delta x. Now what is delta p we have seen. We have given the definition. Now we are going to give the mathematical statement of Heisenberg uncertainty principle using these two conjugate variables. So what is the mathematical statement? What you do is you just determine the product of uncertainties. Simultaneous measurement of product of uncertainties. If you make the product, what will happen? What will be the value? The value will be greater than or equal to h divided by 4 pi. So delta x into delta p greater than or equal to h divided by 4 pi. This equation is known as mathematical statement of Heisenberg uncertainty principle. Remember that delta x is the uncertainty in position and delta p is the uncertainty in momentum. So you know what is the Heisenberg uncertainty principle? What is the mathematical statement? Now we are going to see the significance of Heisenberg uncertainty principle, or I can say what is the actual physical meaning of Heisenberg uncertainty principle. What does it signifies? We are going to see. So the mathematical statement is delta x into delta p is equal to h divided by 4 pi. Now I am substituting the value. If delta x is equal to 10 to the power of minus 10 centimeter, this is the delta x value. If I substitute delta x is equal to 10 to the power of minus 10, after substituting the values, I am getting delta P is equal to 0.5 into 10 to the power of minus 17. So, when you substitute delta x means uncertainty in position. When delta x is equal to 10 to the power of minus 10, what is the value that I am getting for delta P? Delta P is equal to 0.5 into 10 to the power of minus 17. It means when the uncertainty in position, delta x is equal to uncertainty in position. If you compare these two values, delta x is more and delta p is less. Delta x is more means what? Uncertainty is more. Error in the determination is more. So when the error in the determination of position is more, delta p is equal to less. Delta p means uncertainty in linear momentum, that will be less. So when the error in the determination of delta x, when the uncertainty in position is more, the uncertainty in position will be, linear momentum will be less. When the uncertainty of one variable is more, automatically the uncertainty of another variable will be less. Therefore, we can say that if you determine the position accurately, you cannot determine the value of velocity and it becomes uncertain, and vice versa. So, this uncertainty principle is not due to the lack of precise measurement, it is due to the fundamental characteristic of nature, I can say. Therefore, I can say that this Heisenberg uncertainty principle is taking us from classical mechanics to quantum mechanics. Classical mechanics says that both position and momentum can be determined. That is the postulate of classical mechanics. But here, it is not so. So we can say that the Heisenberg uncertainty principle is taking us from classical mechanics to quantum mechanics. Now, one more variable we are going to see. And remember that this uncertainty principle is significant only for small particles, microscopic particles. It is not applicable to macroscopic particles. So the next variable we are going to see, that is known as energy and time. Already I have given you, already we have seen in the examples, energy and time is the second variable. The product of uncertainties of position and momentum, which has the dimensions of h, that can be extended to any pair of conjugate variables. So just as momentum and position cannot be determined simultaneously, the energy and time cannot be determined simultaneously. So this is the definition. As we have given previously, the mathematical statement using these two variables is equal to delta E into delta T is equal to h divided by 4 pi. You know what is delta E? Uncertainty in energy or error in the determination of energy. Delta T is known as uncertainty in time. Uncertainty in time. Now, here delta T is representing the lifetime of excited state. It is also representing lifetime of excited state. See, if the energy of a particular state is stationary, if the energy of the state is stationary, stationary means what? It is fixed. It is fixed. It is stationary. It is living long. Therefore, I can say that if you have energy of a state is stationary, its energy will be low, its energy is fixed, and therefore I can say that lifetime of that particular stationary state will be having higher value, larger value. Suppose if the energy of the state is mobile, mobile means it is not fixed, it is going on changing, it is not stable, I can say. Therefore, it will have higher energy. Higher energy means less stable, therefore, lifetime is less. Therefore, lifetime is less. For example, according to Bohr theory, an electron in an atom goes to an excited state from where it is coming back to the ground state by emitting a photon of radiation. If t is the time remains in this particular excited state, then delta t will give you the error in the measurement of time. Automatically, there will be always an error in the measurement of the energy of the photon and hence the value of frequency as well as wavelength. Now, we are going to see one important application of this Heisenberg uncertainty principle. This principle is very much used in explaining the width of the spectral line, width of the spectrum, I can say. Now we are going to see two cases here. First one is if delta t means lifetime of excited state. If lifetime of excited state is long, what will be the value of delta E? So delta E will be less. If delta T is more, we know that delta E will be less. If delta T is less, delta E will be more. That is the second case. Now we are having an excited state for which lifetime is more. Therefore, energy delta E will be small. Okay. Delta E is equal to h into delta nu. Because E is equal to h nu, if you put delta for energy, delta E will be equal to h into delta nu. Delta nu or delta nu bar, whatever you can say, it is known as bandwidth. It is known as bandwidth. So if delta T is small, delta nu will be also small because it is directly proportional. Delta nu means bandwidth. Bandwidth means when delta nu is small, bandwidth will be small. Bandwidth will be small means what? It means the spectrum will be more intense and it will be sharp. So when you will get sharp and intense spectrum, you can predict the width of the spectrum or the intensity of the spectrum using the Heisenberg uncertainty principle. And similarly, if delta t lifetime is low, delta E is high. Delta E is high. If delta E is high, delta nu will be high. Why? It is directly proportional. So if delta nu is high, bandwidth is also high. So if bandwidth is high, you can say that the spectrum will be less intense and it will be diffuse. Therefore, I can say that the very, very important application of this one is you can explain, you can say that the sharpness or diffuseness that is known as intensity of spectral bands can be explained with the help of this principle. So this principle is very important. The principle, mathematical statement, the application. And these three are very important, and it is more pronounced in the question papers of various universities. Thank you.